All right, so we need to firstly go back over the three states of matter: solids, liquids, and gas. Do know that there are other states that we don't talk about, but these are the fundamental ones, or these are the most common ones that you would see in real life. Solids are rigid, have a fixed shape, and their volume is fixed, so it doesn't really spread around much. Liquids, they're not rigid, so they can move around in different places. They don't have a fixed shape, but their volume is fixed. What we mean by that is the liquid would try to come close together as possible. Similar to a solid, they don't try and space out in all directions quite necessarily. And the last state we have is gases. They are the least dense, so the particles tend to move away from each other. They like to move in all directions. And also, they have no fixed shape. Whichever container you contain a gas in, it's going to try and obtain that particular shape of the container. And it has no fixed volume, because what we know is that gas likes to move around in all directions. It doesn't like to be contained in one spot. So if I show you this, this is sort of a simulation of, or GIF of showing the difference. So on this side here, so we have on the left hand side is gas. As you can see, the gas particles are expanding away from each other or moving away from each other. The molecules or the liquid molecules, they're sort of moving, but not really going anywhere in the container. And then the solid is just still. One of the things you need is differentiate between a gas substance and a liquid substance. A liquid substance does take the shape of the container you put it in, like gas. However, gas can leave the actual container if it's not concealed. And if we look at some of their properties, we'll look at things like density. So how packed is everything together? Solids and liquids, particles are pretty packed together. Gases, they tend to move far away from each other. Volumes and shape, solids already talked about. The same idea here as well. So liquids will try and adopt the shape of their container, but if it's a gas substance, it tries to fill up any free space. So if you have a container and you don't put a lid on top of it, the gas is going to escape outside of the lid or outside of the container into any free space available. Liquids don't quite do that. It just tries to fill up whatever it is contained in. And gas is the only one that you can really compress. And ability to mix, so how well can it mix? Solids, it can't be divided, so you can't really mix two solids together. Liquids, they do mix better than solids because there is a little bit more space, and obviously with a bit of stirring it mixes faster. And then if you have two gases together, or two mixtures of gases, they tend to mix very rapidly because of the amount of free space available. What we tend to say is if something has a fixed shape or volume, harder to have some kind of mixture occurring. If it has a lot of free space and easily compressible, then obviously it will mix a lot faster because there's all this empty space that the new gas particles can go into. So in inquiry question 4, we are looking at how does the ideal gas law relate to all gas laws. We're not going to look into this quite yet today, but we will look into it next lesson. So we're going to try and define a thing called the kinetic theory of particles. We're going to also look at how you measure gas in terms of pressure, temperature. We'll probably look at it a little bit later, and also one I didn't write down is volume. So what is volume to start off with? When we refer to the volume of a substance, it means the shape that it occupies, or how much space is being occupied by this particular object. Now, if we have water, it can occupy a volume of 250 milliliters. If you move it into a different container, as you can see here, the volume remains the same, but the shape is different. So liquids take on the shape of its container, but the amount of space it tries to take over stays the same. It's still 250 milliliters each. But gas is slightly different. Notice if I have a gas column here, and I transfer the gas column over here. Now clearly, based on their shapes, okay, our little measuring cylinder here, the volume of this and the volume of this are not equal. They don't occupy, or they don't hold the same amount of space. In fact, I'd say, based on this diagram, V2 has a larger amount of space for the particles to occupy. And that's kind of what gases do. They still retain the same shape, or their shape retains the borders of the container, much like a liquid, but the amount of space they end up holding on to or occupying is a lot more than a liquid substance. So if I really compress the mass particles down into a really small beaker or something, and I put a little block on that, the gas particles are going to take up the space of that beaker. If I then transfer it back into a bigger conical flask, it will then take up the space of the entire flask. So that's the main difference between a gas and a liquid. The gas actually occupies the same amount of volume its container can provide it. Water only takes up the shape of the container, but doesn't necessarily equal the volume that the container can hold at one go. So what are some ways of calculating units of volume for gas? Reason being, we calculate volume for gases and liquids because it's a lot easier to calculate how much space they cover rather than looking at measuring it on the balance, electronic balance. So you can measure volume in terms of liters, and this is the SI units we use in chemistry. So this is the standard international units we use. Any calculations you do with liters in chemistry, or volume, sorry, in chemistry, always has to be converted back into liters. We have milliliters, and so 1 milliliter is equal to 1 centimeters cubed. What the centimeters cubed actually stands for is we're looking at 3 dimensions of an object. So if I look at my little cube here, I'm looking at 1 dimension here, so that's dimension 1, 1 dimension here, so we can call that dimension 2, and then we have dimension 3 here. So if it's anything cubed, we're actually recording 3 different lengths, or timesing 3 different lengths together. And then we have a cubic meter, and a cubic meter is when we have 1 meter times 1 meter, 1 meter. So we're looking at not only the height, the width, but also the depth of the object when we're talking about volume. And you can also write it in terms of the centimeters, which we already did in the do now question. Okay, so just a little calculation question again, exact same thing as the do now. What you need to do is convert 700 milliliters into cubic centimeters, or centimeters cubed. into liters, and then also cubic meters. So I'll give you 5 seconds before I move on to the actual answers. Alright, so if I want to convert milliliters into cubic centimeters, remember it's a 1-to-1 ratio. So if you times, so 700 milliliters is the exact same thing as saying 700 cubic centimeters. If I want to convert milliliters into liters, you divide it by 1000, so it's 0.7 liters. And if I want to convert milliliters into cubic meters, remember a cubic meter is essentially 1/1,000,000th of a cubic centimeter. So 700 over 1 million, so it's 0.0007, or you can write it as this in the scientific notation. So 1, 2, 3, 4, dot point comes here. That's why we write 10 to the power of -4 here. Next thing we're looking at is pressure. So pressure is defined as the amount of force that's exerted on a surface by a gas when they collide with the surface of the container. So we can have these gas particles jumping around and colliding with this area of space. The greater amount of force, so if we have more force, then more pressure is exerted onto the balloon. If we somehow make the balloon a lot bigger, so if it's a lot bigger, obviously and force stays the same, then there's less pressure on the balloon. That's kind of how tires tend to work. If you have too much pressure on the tires, it means there's too much force coming from the air particles, and it will actually burst the car tires. If you want to increase the pressure on something, you can either decrease the amount of space available, or you can decrease the volume. Because if there's less volume, there's less space for the particles to collide, and so less space, there's probably a great amount of force being distributed. The actual formula for pressure in chemistry is this formula here. So P is pressure. That equals to F, which is the force over area. For those of you who are curious about what units we use, force is given in newtons. We give that a capital N. Area is in meters squared. So pressure is the same thing as saying newtons over meters squared. It'll be Newton meters minus 2. And that's the technical SI units of pressure, though we do use different scalings. That's what it is. The more pressure or the more force that the air particles are colliding to the surface, then the more pressure you have. If the area is bigger, so you have a bigger amount of space, you also have lower pressure. If you decrease the area amount or volume amount, you increase that pressure. If I want to do some conversions, the standard that a lot of people use and that you will see in your data sheet is 1 ATM. Now 1 ATM stands for atmospheric pressure. In terms of how much does 1 atmospheric pressure feel like, it's basically what you're feeling right now. So the standard pressure that you feel on your body, that's equal to 1 atmospheric pressure. If I want to convert it into to pascals, which is another way we measure pressure, it's there. If I want to measure it in kilopascals, there's that. Newton meters squared, that's the one we said is the regular SI units. We also have measurements from a mercury barometer. So that's kind of the early measuring tools they use to measure the pressure or the air pressure outside. And then we also have a bar. So these are 6 methods to measure pressure of gases. Okay, what I want you to do is copy this down into your books, know what these conversions are, and we're going to actually practice some of these calculations in the next slide. So number 4, you have 0.337 bars. Convert that into kilopascals. Next one you have is 253 mm mercury, so it's just a measure of mercury. What's the pressure of the atmosphere in terms of ATM? So what's the pressure in ATM? Last one, you have the atmospheric pressure in ATMs. Convert that into kilopascals. Okay, so the best way of going through these questions is to refer back to our table here. Okay. So I'll give you a minute or so to work on that. What I'll do is though, pause the video here. I'm going to move on to the next couple of slides in 5 seconds. Cool. Alright, so if you want to convert bars into kilopascals, times it by 100. So you have 33.7 kilopascals. If you want to convert the pressure of mercury into atmospheric pressure, it's 253 over 760. So that's your answer there. And also our final question, how much is this in kilopascals? 33.7 kilopascals is my answer here. Alright, so an interesting thing we also know about pressure, not only is pressure defined as the amount of force that gas particles can exert in an area of space, but we can also calculate what's the total amount of pressure exerted by a mixture of gases if we just include the initial starting ingredients. So let's say air is a mixture of multiple types of gas. You have nitrogen, oxygen, carbon dioxide, and argon. These are some of the most common ones. Let's say I found the individual pressure that's exerted by oxygen, or the partial pressure exerted by oxygen. I found that in a temperature of 20 degrees Celsius, oxygen exerts a pressure of 20 kilopascals. And then I look at the same thing in the same temperature for nitrogen. Nitrogen exerts about 80 kilopascals. If I mix these two gases into one, and imagining it's in the same container, no gas has been leaked during this mixing process, I have the same amount of particles of oxygen and nitrogen inside the same container volume. So the area of the container hasn't changed. The only thing that has changed is I now have more particles, and so the amount of force exerted has increased on this glassware. And what we end up finding is the total pressure after the mixture has occurred is just the sum or the addition of the original two gas substances. So oxygen is 20 kilopascals, nitrogen is 80 kilopascals. The total mixture, or the total pressure of this mixture, is just 80 plus 20, 100 kilopascals in 20 degrees Celsius. we can write that up there as a general formula. So we can say the total pressure of a gas mixture is given by the partial pressures of one of the gases, one gas sample, and then another gas sample. How is partial pressures worked out? Remember, you can work out the area of your surface. You can also work out the amount of force that each particle exerts, or as an average, what each particle exerts. So I can work out the partial pressures of my two ingredients, we could say. Mix it together, and I'll find out the total pressure of that system. So there's that. Let's move on. So that's what we have. Now, in terms of measuring pressure, how have we done it? One of the methods that we can talk about is this Mercury column. Okay, what actually happens is, based on one of the gas laws we will talk about next, is if you have a dish full of mercury, not that you would normally see someone with that, but you say you have a little dish full of mercury and you have a little column tube. You put that column tube into the mercury. What actually happens is the air pressure from the atmosphere will push down on this mercury fluid and will actually push up this column tube. Now, why exactly that happens, we will talk about with the upcoming gas laws, but it actually pushes the tube up, gets further up, and that actually tells us the current air pressure. So under normal conditions, let's say if we are on the surface of the Earth, and I measured the column here, I'd find that this mercury would reach a scale of 760 mmHg. So about that much quantity of mercury rises up. If I went up to a place that's really high, so let's say Mount Everest, so Mount E, and I did the exact same thing, what I'd actually find is they always say to you that when you're in really high altitudes, the air becomes really thin. Well, that statement holds true because when you're really high up, the amount of gas, or the amount of pressure exerted by the gas, is actually less. So less is exerted at a really high point. And so what actually happens is you end up getting a much smaller column. So the column doesn't actually reach as high. If you went to the center of the Earth, obviously it's a lot, the pressure or the air pressure is a lot higher as you go further and further into the Earth. So you would see this column here rise up again. So in high altitudes, air pressure tends to go down. And if it's low altitude, it tends to rise back up. This is a little video in terms of the history of how a barometer was created. It's just a TED video. I will link it to you in the Google Classroom and also the comments below here. So make sure you spend just a couple of minutes just watching how it works. It gives you a bit of context of the current topic, and just like a little nice application to what we're doing so far. Next thing we have to talk about is the kinetic molecular theory. Now, kinetic or kinetic energy is essentially energy based off moving particles. So if anything is moving, if you are walking right now, if you're running right now, you'll have kinetic energy. And the formula for kinetic energy is half mv squared. M is mass. So m is the amount of mass an object has, and v is just the velocity. So mass and velocity here. One of the things that a lot of you might not know is temperature is just the average kinetic energy of a system. So when you're talking about the type of temperature that's inside your body, that temperature is actually a calculation of the average energy all the particles inside your body is moving. So that's what temperature means. If someone tells you they're releasing a lot of heat energy, that's actually not the same thing as temperature. Temperature and heat are not exactly related to each other, but average kinetic energy is essentially what temperature means. So if we talk about the model of kinetic theory, so we're looking at the models of particles and how they move, we notice a couple of things, and this is what we call ideal gases. So we're saying an ideal gas, right? An ideal gas particle loves spreading apart, so they like moving away from each other. So all these particles, they kind of move in all different directions, all random directions. You can't really predict where it goes, but it's very random, and they like to go as far away as possible from each other. What you'll also find is they tend to collide with each other a lot too. So they will collide with each other in one spot here, and then they'll collide to each other in one spot here. There are some general assumptions we can make about these models, and it actually explains to us a lot about what actually happens in real life applications, which I'll show you very soon. So that's just another diagram to show you. You can read through that in your own time, taken from NASA. So this is just the assumptions that we make with the kinetic theory model. So I need you to copy this down, but I'll just go through basically what each one stands for. So the first assumption we make is all gas atoms or molecules are in constant random motion. So they're always moving in some random motion. You can't really predict. They're just moving in all separate motions. They are also doing this in a straight line. So they tend to like going in straight lines. They go this way, or they go that way, or they go that way, or they go down like that. So always straight line, random motion. They don't kind of curve away. That's not how it works. So not like that. The intermolecular forces between gas particles are negligible. So what that means is if you have a little particle here and a little particle here, right, we're not going to worry about how attracted they are to each other. We're just going to say it's so small that virtually there's no attraction between the gas particles or the gas molecules when they're inside a container. The size of the particles is tiny in comparison to the distance between them. It means they are here, and then there's this massive vacuum of space, essentially. We also make the assumption that when these gas particles collide, we have a perfect elastic collision. So a perfect elastic collision is when you have two objects that smack right into each other, and then they kind of bounce off each other straight up like that. We call this kind of collision elastic because they essentially bounce off. There's no transfer of energy. No energy has been lost. Now let's say you have your two hands together and then you just clap your hands. We try that. Okay, and that's an example of an inelastic collision. Why do I say that? Because when you're clapping your hands are moving. That's kinetic energy. When they hit each other, there's some form of deformation in your hand. There's a little bit of vibration. So that's already showing that some energy has been lost due to deformation of the hands. But also, if you clap, you'll hear sound. That also shows that some of that kinetic energy has been converted into sound. So it's not perfectly elastic. We haven't retained the same form of energy. We've essentially converted it into something else or transformed it to something else. We also said that the pressure is a result of collision between gas molecules and the surface. So we already talked about that. That's just P equals to force over area. We also said the kinetic energy of the particles is directly related to or proportional to temperature. Remember, temperature is the average kinetic energy of the system. And number 7, I just realized I've essentially repeated myself in point number 2. So please make sure you copy these 6 points. You can not write point 7, but just write point 1 all the way to 6. That's just to keep you up to date what kinetic theory is.
And that concludes our lesson today, where we talked about the different types of properties of gases. In our next lesson, we're going to actually start looking at ideal gas laws. So what we brought in today about the kinetic molecular theory, we're going to be applying that to the 3 gas laws: Bohr's law, Gay-Lussac, and Avogadro. Until then, I will see you next time. Oh, let's not forget Charles' law as well. But yeah, until next time, take care.